Okay, find the indefinite integral, so you know you're going to have some plus c of some sort, and check the result by differentiation. We don't have time to check it, but if you wanted to check it, take the derivative of your answer, and you should get the original integrand that's right there. Okay? Now, I look at this problem, and the very first thing that I see is that there's one term in the numerator. And you're trying to build your awareness from my experience, okay? Without having to do 30 problems. I'm looking at this and I see one term in the numerator. The fact that it's not a constant says that I won't bring this up for a rewrite to a negative 3 power. I won't, okay? It will be easier other ways. If there was one term on the bottom, I might consider of breaking this up into 2 fractions if there was one term like this, adding or subtracting. That's not what I have here. So now my third go-to, if you will, is going to go straight to U substitution. Okay? I see a big parentheses pieces that I can substitute for U. What parenthetic, the biggest parenthetic piece that you can find? 4 minus 4x squared. Okay? So where 4 minus 4x squared used to be, let me write the original equation. Where it used to be, I'm now going to put the letter what? U. So it's going to be U, and everything else is original, to the 3rd power. Okay? What have I not accounted for yet? That's from the original integrand. The x up in the numerator, and also the what? The dx. So what I'm going to do is I'm going to take the differential right here of deriving both sides, almost implicitly. If you see u, it's du. If it's w, it's dw. Okay? If it's x, it's dx. It's no longer just x is going to be 1, or you know what I mean, as far as the coefficient going out. So what's the derivative of the right side? Negative 8x times dx. So it has a chain rule piece to it, okay? So if you have this negative 4x squared, it's going to feel like you're doing a chain rule. So it's like something that's going to look like that, if you will, that you have to multiply by the derivative of the cream at the end. Okay, so it's that Oreo cookie analogy. So it'll be negative 8x dx. Because you got to multiply by the derivative of the chain. Are we good? So now, you said the piece that we did not pick up was x dx. And guess what? It's sitting right here waiting for you to use it. We're going to substitute here in just a bit. So wherever x dx used to be, I'm now going to put, watch what I do, divide both sides by negative 8. So we get negative 1/8 du is equal to x dx. So now guys, where you used to have x dx, you're now going to write negative 1/8 du. This is that substitution. Real quick, because some people don't know. If I multiply this with this, is it the same thing as writing that? Yeah, so that is the same thing. So those are going to be in the numerator, just like this is. So I'm going to replace it with negative 1/8 du. Why do I have this negative 1/8 outside? Constant multiple rule. What should be in my numerator as an understood? 1. Should I integrate now or try rewriting before I integrate? Rewriting. Why? Because there's one term in the numerator and it's a constant. So I'm going to rewrite this as, let me go ahead and do it here, negative 1/8 integrating u to the negative 3rd du. Now I'm ready to integrate. Okay? And once you've integrated, remember, these two pieces here, the summation and the du, they'll disappear once you've integrated. You've taken the antiderivative. Help me out, guys. What does u to the negative 3rd become when I integrate it? U to the negative second over negative 2. The new power, right? We do have to multiply our constant back in, which is a negative 1/8. And we still have to do what? Add c. So my running answer as it stands right now is going to be u to the negative 2 over 16 plus c. Some of you will write 1 over 16, and you don't like those negative powers, so you'll move it back down, and you'll see something like that. Notice how it's really close to my answer. The only difference that we still need to do is that our answer is in what of u? It's in terms of u. But I need my answer to be in terms of what? X. So I'm going to use this original u substitution, plug it back in right there, and that's how you get your answer that you see. So it's almost like you're borrowing a variable so that you can reassign the entire integrand to make it a lot easier, so that you do a lot easier of an antiderivative, and you get to the answer. Yes?
Is it always going to work out like where when you solve for du, it'll always be somewhere in the equation?
Yes, this is a really good question. The question is this: when I assign u, will it always work out to where the pieces that you need here in green will be the pieces in the original equation that are left over? The answer is yes, most of the time. We're going to do enough examples so you'll see what else you have to do other times. Okay, but notice how I did this dividing both sides by a negative 8. It's a lot easier to see. I'm going to replace it with a negative 1/8 du by doing that than if you were to leave the negative 8 over here by itself. That's harder to see because I'm just trying to replace letters with other stuff. Yes? Any other questions?
So, could you explain why you put negative 1/8 and put 1 in the numerator and substitute du?
The reason why I pulled this out, this is another good question, is when I take the derivative, I know I can take the derivative of a constant. It's going to be 0 no matter what. But when I take the antiderivative, I don't have to take the antiderivative of a constant per se. I just have to multiply that constant back in. Basically, everything here that's going to be in the machine. Let's envision this integral as a machine. When you turn it on, these pieces go away and you don't see them in your answer. And this is the reverse power or whatever it is. Notice your integrand, all these pieces here are all just variables. You with me? Ultimately, that's what you want to do, because it's easier to see it that way and account for the constants at the end. And you'll see through practice.
Yeah, my question is, so the du just disappears once you get to that last step?
Yes, it just disappears. Once you integrate it, what happens? Theoretically, what is happening is that this du, remember when we did Riemann sums? And I said, what width of these rectangles would create the perfect area where there's no overage? What would the width be? Approaching 0, right? We're wanting that to approach 0. So this notation here of du is representing this part right here of a rectangle. So the du right here is representing the du right there. It's the width of the rectangle. And it's infinitely approaching 0 as you're taking the summation, basically adding up infinite rectangles. So it's doing the Riemann sum, but not with 4 rectangles, not with 6 rectangles, with infinite rectangles. So theoretically, that's why it disappears, because you've done the process known as taking the integral.
Alright, that makes sense. I just thought it just kind of went away.
Yes?
So, I'm so confused why you put the 1 in the numerator whenever you use
Oh, because it's just understood. So, like, let's say that I have 2 over x. And I pulled this 2 out. What would be left over in the numerator? It'd be a 1. That's where that 1 came. It's an understood one through multiplication.
So where did the x go?
This here, you're asking?
No, the x at the top in the original equation.
Oh, okay. So finally, and I think this is probably the last question that most people have, is where did the x go? Remember, the x dx has now been replaced with negative 1/8 du. So here, negative 1/8 du is where, on the original problem, x dx used to be. This is why we're substituting. So we're just like you did with systems of equations a long time ago when you did substitution. A lot of us did elimination because it's faster, but when you did substitution, it's the same thing. You're plugging in something for a different variable to make it all a different variable or the same variable. Okay?